Hello, welcome to Math-166 Business Calculus. Because we have a quiz on Wednesday, I would like to devote the majority of the time Tuesday on our quiz review. And I didn't quite finish up section 1.4, so the purpose of this video is to do a quick recap of section 1.4 and complete 1.4 so we can spend the day Tuesday on our quiz review. So we were talking about functions. And just a quick reminder, when you're using your calculator for the distance formula, don't try to do any math where you do fractions or anything. Enter the whole thing using parentheses properly and just come up with the correct answer on your calculator. The less math you can do mentally, probably the better. So we're going to look at the difference between a function and a relation. Remember, a function passes a vertical line test. The domain are your x's from left to right, and your range are your y's from bottom to top. So first, talking about functions, for every x there's a y, and remember it doesn't have to say f of x is equal to or y is equal to. It might say something else. The most common function that we've seen so far is a linear function, and so this of course graphs a line. So you should kind of recognize the different types of functions. We talked about x being the independent variable, the y being the dependent, and that will help us when we start graphing. So time is usually the x-axis, and then money is the y-axis, and that's because money, the y, depends upon your x, time. So time is the independent variable. So you could think about it as the domain, the x's are your input, and your range are your outputs. We also talked about y depends upon x and graphing these functions. You can identify a function really quickly if y is by itself. So this is yes, it is a function. This is no, because when you take the square root of both sides, you'll end up with y is equal to plus or minus. And for every x, there's not just one y. So this is a big no. This y is by itself. So yes, this y is being squared. So no, that's not a function. Incidentally, if that would have been y cubed, then I would be back to yes, because you can take the cube root of 8 and get one number, and you can take the cube root of -8 and just get one answer. It's only when you take the even root do you end up with plus or minuses. So we'll slide through these examples. Here comes the vertical line tests. You can see if the function only crosses once, then yes, it's a function. This is a no. This is a yes, because every time I draw a vertical line it passes, but this is a no, not a function. The domain, again, are the x's. The range are the y's. If I don't graph the function, you can tell this is undefined for those values that set the denominator equal to 0. So I don't really care about the numerator, but the question is, when does x squared minus 4 equal 0? And that's when x squared is equal to 4, or that's when x is equal to plus or minus 2. So I'm having problems at positive 2 and negative 2. So I would say the domain is all reals, except you would have to exclude positive 2 and negative 2 because you don't want to divide through by a 0. If it's the square root, remember you want to take the square root of a positive number. So instead of setting this equal to 0, I would say this x minus 1 has to be greater than 0. So x has to be greater than 1, and that would be my domain. In the second example, this is called a piecewise function, and for all the values of x that are less than or equal to 1, this is always defined, and for all the values of x that are greater than or equal to 1, this is always defined. So I would say the domain is all reals. It goes from negative infinity to positive infinity. There's no place that I would end up with an undefined value, because this is always all reals, and this is all reals for all those values of x minus 1 that are greater than or equal to 0. That means x has to be greater than or equal to 1, which it is, so it's always all reals. To find, and then we could talk about the bracket versus the parentheses. For part A, since I can take the square root of a 0 and get a 0, I can actually let x equal 1, and I'll be fine, because the square root of 1 minus 1 is the square root of 0, which is a number. So I can include the 1 in part A, opposed to me not including the 1 in part B for the first one, or for the first piece of the function. So there's domain. Here comes the range. So it's a little bit easier to look at the actual graph of the function. There was a line and there was a square root function. But the range would be from bottom to top. So it goes from 0 to infinity. And that would be the range. A one-to-one function means not only does it pass the horizontal line test, it also passes the vertical line test. So it passes both. And that's called a one-to-one function. Function notation is f at x. It's pronounced f at x, and sometimes we write y. So to find out if something is a one-to-one function, I need to make sure that for every x there's only one y, and for every y there's only one x. The suggestion is to test all of these points, or all three of these points, and see if there's any duplicates. And to save time, you can see that there is a duplicate, so it's not a one-to-one function. Again, it's easier to see. It passes the vertical line test, but it does not pass the horizontal line test. This slide is saying that you can replace a y with f of x. This slide is saying that you can evaluate x at any point by just plugging in some value for x. We practiced this in class. This is called the difference quotient, and it will be on your quiz. So f at x plus, I would replace delta x, change of x, with h. It seems like students are a little bit more successful if I just put a variable instead of going delta x. So my definition looks like this. So I'll go go find f of x plus h by plugging this into my x value. So instead of getting x squared plus 7, I'll plug in an x plus h. And again, my big pet peeve is don't distribute that 2 throughout. I'll actually square the first, twice the product, square the last, and replace all of this with f of x plus h. So I'm going to write this problem down. This is my x squared plus 2xh plus h squared plus 7 minus the function, and the function is all of this, x squared plus 7, all divided by h. Don't forget to distribute the negative. I'll rewrite the whole thing again. X squared plus 2xh plus h squared plus 7 minus x squared minus 7. And if you've done this carefully and correctly, some nice things should cancel. Looks like the 7s are gone and the x squareds are gone. And then from the numerator, I can factor out an h. So pulling out an h from these two terms, I have a 2x plus h that's left. And I can cancel the h's, leaving me with 2x plus h. And here's how the author chose to solve this. And they got the same thing. Remember, h is delta x that we replaced with. And we gave a second example. You can try that on your own. So here's where I left off, and this is the new material. Combinations of functions, or composite functions. We can add functions, we can subtract functions, we can multiply functions. Some of you know as FOIL, and then we could even divide functions, but oftentimes if you do the f at x divided by the g at x, remember you cannot cancel part of a sum. That's another thing that students always try to do that I want to impress upon you that you cannot do. You cannot cancel part of a sum. I get pissed off at students when they try to cancel part of a sum. So that's a big no as well. Composite functions are functions within a function. Sometimes it's written f of g at x. This does not mean multiply. That's an O for of. You could think about it. But it's written f of g. The first thing I would do is if you see f at a g at x, I would rewrite it as f at g at x. You pronounce them the same. And that's a composite function, a function within a function. So again, here's the notation. So for this one, I would go ahead and just write the g at x function, which is x squared plus 1. And then this says go to the f function and plug that in. So instead of 2x minus 3, replace the x with parentheses, and then write in the parentheses what it's supposed to be, and in this case it's 2x plus 1. And then distribute. 2x squared plus 2 minus 3 is really 2x squared minus 1. Going the opposite direction, let's write down the f at x function, which is g at f at x, which is 2x minus 3. This says go to the g function. And again, the key here is to replace, God, I'll write it out. Students just don't want to do this. X with parentheses. Why don't students do that? So instead of writing x squared plus 1, it says go to the g function. Instead of writing x squared plus 1, write parentheses squared plus 1. This is the step. I don't know why students skip it, but would you please just do it? And then you plug this in. I don't know what's wrong. Students find that they're skipping too many steps, and they don't like to write things down, and then they make mistakes. Well, remember, this is the trap again. Can't distribute. So the rule is square the first, twice the product, and the product of 2x and a negative 3 is negative 6x, and I'll double it. Negative 12x plus 9 plus 1. So this final solution is 4x squared minus 12x plus 10. So for composite functions, replace x with parentheses. And then again, here's the author's work. And it looks like they got the same thing. Yep. Inverse function says replace your x's with y's and replace your y's with x's. So the inverse of the point 3 comma 4, which remember is your x and your y, the inverse of that would be 4 comma 3. Simple concept. Inverse functions are denoted as f to the negative first. Be careful, that does not equal the reciprocal function. I know that's weird notation because x to the negative first is 1 over x, but this is not true. You cannot reciprocate it. What this is saying is if you do have an inverse function, if you take f of the inverse function, you'll get x. Or if you take the inverse of a function, you'll also get x. Let me show you how that works. It says find the inverse of each function. So remember, this is y equals 2x. So to find the inverse, I say x equals 2y. And then remember, you have to solve for y. So you can do that dividing both sides by 2. So y is equal to 1/2 x. Now, keep in mind that's the same thing as x over 2. So you can write it either way. But I would like for you to get in the habit to see that I'm replacing this y with the inverse function because I don't want to get that y mixed up with the original y, which was the original function. So let's try that again. Here, f at x really is y. To find the inverse, I replace y with x, and I replace x with y. But remember, you have to solve for y. So I can do that by subtracting off 4, x minus 4, and then I'm going to replace this y with the inverse function. To verify that these really are inverses of each other, I can do the composite functions. I can check f of f inverse of x and see if it equals x, and I can check f inverse of f of x to verify that it really equals x as well. If they are inverses of each other, you'll have these nice 45-degree y equals x. So you can graph them to find out, to verify if they're inverses of each other. But to verify that something is an inverse, you can check the composite functions. So let's try this one. If y is equal to the square root of 2x minus 3, then the inverse of that would be x is equal to the square root of 2y minus 3. Well, to solve for y, I'm going to have to square both sides. So x squared is equal to 2y minus 3. I'll add 3. X squared plus 3 equals 2y. And the last thing I do is divide everything through by 2. So the inverse of this function is x squared plus 3 divided by 2, which keep in mind is the same thing as 1/2 x squared plus 3. I don't know why students don't see that that's equivalent, but it is. So the next thing we're going to do after we agree that that's the inverse of the function, which it is. So here was the original function. Here was the original function, and here was its inverse, which is what we just solved for. Now we're going to actually prove, well, we've graphed them, and so you can prove that they are inverses by looking at their form. But we can also prove by checking two things. Let's go see if f inverse really is x. So the function is given, and we found that this was the inverse function. So I'm going to plug that in, and it's x squared plus 3 divided by 2, and I'm going to check to see if that really does equal x. So this says go to the f function and replace x with parentheses. So go to here and say the square root of 2 times parentheses minus 3. And then in the parentheses, you plug in the inverse function. In this case, x squared plus 3 divided by 2. Those 2's will cancel. I'm left with x squared plus 3 minus 3, which is the square root of x squared, which is x, which is what I was trying to prove. So I have to do this twice, though. I also have to check f inverse of f at x and see if that also equals x. So the proof is kind of a two-part proof. So this time, I'm going to actually start with the function. So this time I plug in this, because that's f at x. So that's the square root of 2x minus 3. Now this says go to the inverse function, which is right here, and replace x with parentheses. That's the important part. So instead of x squared plus 3, I'm going to do parentheses squared plus 3 and divide it by 2. And then in the parentheses goes the function, which is the square root of 2x minus 3. And the square root of anything being squared is just itself, so 2x minus 3 plus 3 divided by 2. All of that goes to 0, so this is really just 2x divided by 2, which is just x. And again, the proofs look different. Your left side proof should look different than your right side proof, but the results should be the same. They should all equal x. So that's how to prove a function is the inverse of another function. And here's the author's way of working through that. Not every function has an inverse function. In order for a function to have an inverse, it has to be a one-to-one. Remember, a one-to-one means the vertical line test pass and the horizontal line test pass. Here is an example where it does not have an inverse. And you could try that same f at f inverse of f at x and see if it equals x, and test f of f inverse and see if it equals x, and it won't happen. The easiest way to do this is just to graph it and see, hey, it doesn't pass the vertical, it passes the vertical, but it doesn't pass the horizontal line test. And you can check some points and see that that doesn't work. So because the definition of a function is for every x, there's only one y. When you take the square root of both sides to solve here for y, you get two solutions. So recapping this really quick, you can identify whether it's a function or not if there's only one y. So this is a no, no, yes, see, because it's to the first, yes, yes, no. This is a function, there's only one y, so it's y to the first, and this is a tricky problem, but I suppose it'd be yes. It is a function because there's only one y. Vertical line test, no, it doesn't pass. Yes, it does pass. Yes, it does pass. No, it does not pass. The domain here would be all reals, because this goes forever left, forever right, and the range would be all reals as well. The domain here is, probably 1.5 to infinity, and the range would be the bottom number from 0 to infinity. And then I would finish with all of those. It looks like the range here goes from negative infinity low up to 4, and I would probably include the 4. When you run across a problem like this and I'm asking for the domain, it would probably be all reals, except x can't be in the denominator, negative 4. And then here you want to make sure that 9 minus x squared is greater than or equal to 0. So negative x squared is greater than or equal to negative 9. Remember, when you divide through by a negative, that inequality sign flips. So x has to be, when you take the square root, less than or equal to 3, or x has to be greater than or equal to negative 3. Again, you might want to graph this, and I'm guessing that the graph looks something like this. So maybe if you put it into your graphing calculator, you'll be able to identify domain and range a little bit easier. So the rest of these book problems are practicing with the difference quotients and composite functions. So you're welcome to work through those. I hope this video was helpful. Email me with your questions. Thanks.